So, welcome back student. We are basically discussing that several kind of mechanism based transformation will help you to access medium sized target molecules, and you said that if you are quite familiar of some important mechanism or mechanistical aspects of certain transformations, that will help you to design the retrosynthetic pathway very efficiently. So, next target which you are trying to do it right now is a very interesting one, and this basically combination of transformation as well as starting material as well as functional group also will be trying to combine the three strategies together. In addition, the mechanism which is very important and plays an important role in designing the effective pathway will be trying to focus in this particular problem. Now, initially let us give you the target structure. The target structure is the target structure is the structure is wrong. So, we will draw it again. The 6 member and 5 member based target, we are having a angular methyl in the ring junction having a cyclohexanone, and here you are having a CO2 Me group. Now, you say this is the target molecule, the starting material was also given to you for your better understanding. This starting material is named as polygon, is a easily available raw starting material or raw feedstock. So, basically it is C10 carbon containing molecule is a terpenoid. Now, if you see the target and the starting material, initially it will be in little bit difficult scenario, because this target and the starting material, you see that this functional group, extra functional group like methyl has to be introduced here, 1 methyl extra, then CO2 Me, and you have to form the ring. So, then you may think that though okay, it is a probably a different ball game together. Now, do not get nervous, we will try to analyze through its individual retrosynthetic pathway, and now we will try to do the retro based on the target structure available and how this target will we can try to access it, and we will try to correlate with this starting material which was given to you. So, initially we said if you can have this we are having again some problem, the starting methoxy will be here and this will be the methyl one. So, target structure was basically a bit sorry for drawing the wrong structure. So, this is the target structure. Now, I say if you have this molecule and you initially, I said this is angular methyl of these things will be trying to introduce through a cyclopropane cleavage, the mechanism which we just explained in the earlier slide by a simple FGI through a Birch reduction or sodium liquid ammonia reduction. Okay. And we said this cyclopropane can easily be constructed through a Simon-Smith kind of cyclopropanation. So, now try to get the these things and this methyl. Now, we are saying that okay, this Simon-Smith is fine, but you need to access this alpha beta unsaturated ketone and so we will be doing it from a alpha beta unsaturated alcohol. The remaining part of the other structure is all similar. Now, say alpha beta unsaturated ketone, we can simply do a disconnection based on a known reaction, which is our Luche kind of reduction, and then this Luche kind of reduction will basically the same intermediate. Okay. Now, if you correlate, that this methyl is here, this CO2 Me is here, and now we are saying that this particular ring will be making through a Robinson annulation, which was earlier discussed to you, CH2, because we will be just now making this particular bond through a Michael aldol reaction. So, you need CH2, you need a CO here and this methyl. So, you say this is a standard Robinson annulation. Now, do the next round of retro, and we are saying that we will be disconnecting here to basically give you a methyl vinyl ketone, just by a methyl vinyl ketone. So, methyl vinyl ketone is commercially available. Now, you need to make this particular starting material, which was here through this compound. Now, I say the cyclopentanone, which is be one of the intermediate, how you can construct it. Which is this cyclopentanone compound, you might be thinking of making through a this compound. Now, I am by a ozonolysis reaction, and then we are now closing it here to the starting material, which is polygon. Now, this transformation, can you getting some hint? This transformation basically you can use a Favorsky type of reaction. Now, Favorsky reaction, as you said, is a ring contraction reaction, but also you need to think about that how this Favorsky reaction will be doing it here. So, first take this starting material. Initially, we will be using bromine in carbon tetrachloride. Now, this bromine in carbon tetrachloride will basically brominate the double bond, the isolated double bond, to give you corresponding dibromide species. So, Favorsky always we said that you need a alpha bromo ketone. Now, we react with sodium ethoxide or sodium methoxide. Here as it is the ester is methoxide ester, so use a sodium methoxide. Now, once you use the sodium methoxide, initially this carbon ion will be generated and this will react with this bromo to give you the cyclopropane intermediate in the Favorsky reaction. We are having this Br here, this is the methyl. Now, see your OMe is already there, which act as a nucleophile, and then you will basically getting a O minus OMe and then this Br is there. The cyclopropane will now be cleaving. Cyclopropane will now cleave. Now, cyclopropane basically can cleave in different way. Once cyclopropane is cleaving, it basically either can cleave in this bond or in this bond. But if it cleaves in this bond, you get a negative charge here, and this negative charge is now getting a bromine in its adjacent position. That basically, so bromine is a good leaving group, all of you know. So, what we are trying to do, you basically now cleave this is a modified Favorsky reaction. Whenever you are having a leaving group, the ring cleavage is basically now taking place. So, we will try to put the cyclopentane in this way, this, the methyl is here, and after this cleaving it basically gives you. So, methyl and CO2Me now coming to adjacent, and then you basically after this particular bond cleavage you have this negative here. So, this negative now triggers the elimination of this bromide, and once this bromide elimination takes place, you will now get the compound which you are looking for. MeCO2Me remains there, and then you will basically getting this compound. So, it is the reaction basically goes in one shot, this cleavage, this bond directly transfers here and bromine is liberated. This is nice demonstration of Favorsky reaction, where initial starting material having this polygon with a isolated double bond, and this isolated double bond first you are brominating to make a dibromo species. Now, once this dibromination takes place, you then start with the Favorsky reaction. So, Favorsky reaction now give you a initial cyclopropanone intermediate with this bromine remains here. Now, this O-methoxy attacks the cyclopropanone and you get this compound. Now, as I said, the cyclopropane cleavage will now be taking part on that side, because a bromine is there. So, it can now quench this negative charge which has been generated. The negative charge will be now forming a pi double bond. So, now this is the intermediate same. So, now what you do is simply take this intermediate as we have drawn in the earlier slide. CO2Me is here, you put this. Now, do a simple ozonolysis. A simple ozonolysis will basically give you the cleavage of this double bond, and you will be generating the beta keto ester. Now, beta keto esters are very good substrate for Michael addition. So, now you are having methyl vinyl ketone. So, this carbon ion can be easily generated and reacts here. So, now basically what we will get? You get this methyl CO2Me, CH2, CH2, write this double bond of ketone and this way. Now, this CO2Me is basically your angular CO2Me, which is created after the ring fusion. Your carbonyl group remains here. So, now you do the aldol. So, Michael aldol combination is your Robinson annulation. So, it will be basically here your CO2Me is angular, your methyl is angular. Now, no need to do the Lucci reduction as was given in the original slide. Actually, in the original problem the stereochemistry was given. So, as stereochemistry was omitted, you can simply now do the Simon-Smith reaction here. The Simon-Smith reaction will now give a cyclopropane. The cyclopropane will be generated here, and then everything is pretty much set. Now, what you do? You just do a Birch type of reduction, lithium liquid ammonia or sodium liquid ammonia liquid, and then you ensure that this single electron basically cleaves this bond, which we explained earlier, to yield you the compound which is now the desired molecule you are looking for. The methyl comes here, the CO2Me is there, and this methyl is here. So, eventually if you are not quite familiar of this Favorsky reaction mechanism, it will be bit difficult to visualize the main thing. That is why I said, if you come to this intermediate by conventional retro, now you have to link with how this intermediate can be correlated with this starting material through a Favorsky reaction. A normal Favorsky reaction is fine, always you can start taking alpha bromo ketone and subject it to base, but here the starting material having a extra olefinic unsaturation. That is why the bromine dibromination we do it here, these things and these things. Then once you generate the carbon ion, that will be giving the cyclopropanone thing. Now, one bromine is still there. Now, this bromine helps you to cleave the cyclopropanone towards its direction. The regiochemistry now basically fixed, because this bromine can undergo elimination with this newly generated negative charge, and then the ring fragmentation of the cyclopropane basically goes through in this way, and then you can come to here. Now, once you come here, the relative part of the remaining part of the synthesis was absolutely simple, and then you can simply quench the reaction mixture. You can get this product, do a ozonolysis, come here, do a Michael addition with methyl vinyl ketone followed by aldol, that gives you the alpha beta unsaturated thing. Your CO2Me and methyl is in their respective position. Now, do a Simon-Smith reaction with diiodomethane, cyclopropane, then you just cleave it with lithium liquid ammonia to complete the synthesis. So, this particular synthesis is very useful, where we have discussed several transformation. We talked about a Favorsky transformation, but this Favorsky reaction or Favorsky rearrangement was absolutely crucial for this particular pathway, as the initial bromo compound was not given. You have to generate the bromo compound by a dibromination. So, one bromine undergoes initial Favorsky reaction to give you the cyclopropanone, the remaining bromine was essential for your another pi bond creation, which will be then ozonolized to give you the ketone. You also use a Robinson annulation, which is nothing but a Michael aldol combination. You do a Simon-Smith type of Simon-Smith reaction to give you the cyclopropane, and then finally you do a Birch type of reduction, to cleave the cyclopropane to complete the synthesis, where you will be creating the methyl on the beta position, that we explained that how it can be done. So, in this way a combination of a useful transformation can be very helpful and give you the desired target. The next one what I am going to say, it is a simple one, but will be the target is this molecule. When I say you have to use this as a starting material, simple cyclohexanone. Naturally, in reality you can do a very straightforward retro. You say that okay, I will be having this compound. So, if somehow you can have a X here, which you can on X means Br or iodo or something else, you can do a elimination here. That is definitely possible. So, initially you need, if you having a this compound where you can introduce the bromine. The point is the regiochemical issue is a big issue, because your beta position is already blocked by a bulky isobutyl group. Now, introduction of a electrophilic bromine iodo or a bulky group like seleno pH may occur from this place, not from this place. So, this pathway has a serious regiochemical concern. The regiochemical issues may not be solved if you use this pathway. Now, this compound, as I said, you can easily construct it by a simple Gilman type addition if you having a this kind of copper lithium. But as I said, if this position is blocked by a bulky isobutyl group, your introduction of this electrophilic bromo or iodo to alpha to the carbonyl may occur in this position, not here, and then you get a this product which is not the target molecule. So, here is there a other way? We say let us try to draw the starting material and formulate if there is a other way. Sometimes you can think about a very unusual nucleophile which normally we do not use in a nucleophilic substitution reaction. We say triphenyl phosphine might be a suitable nucleophile, the phosphorus might be a nucleophile. Now, why triphenyl phosphine was used, that is a tricky question. We all know triphenyl phosphine kind of compound are a good source to generate the corresponding phosphonium species which helps in the Wittig reaction. So, here what we are trying to do, we will say that we will be using this triphenyl phosphine as a nucleophile and use a TBS chloride. Now, TBS chloride, why what it was used? First, this undergoes a Michael type addition. So, now this triphenyl phosphine becomes P plus and this basically comes here. So, we are having this O minus. Okay. So, initial generated enolate comes to this position. Now, this O minus you are having TBS chloride. So, this is a ready for enol ether formation. You have this O Si methyl tertiary butyl and the chlorine here can now neutralize the triphenyl phosphonium salt. So, now what is this? This compound is basically a Wittig salt. It is a Wittig salt, it is a allyl Wittig salt. This is absolutely, now we are saying that we will try to now introduce this compound as a Wittig salt and we will try to react with some of the aldehyde. Now, what functional group you require on this point? You need a isobutyl group. So, we will be using a this particular aldehyde, isobutyraldehyde here for this Wittig transformation. Now, as I say, this is not a very unusual, this is not a usual transformation, it is kind of an unusual thing, but still it gives you very nice approach. So, now we are basically making this compound. Okay. Now, try to correlate with this target, target was basically this. So, this enol silyl ether now needs to be hydrolyzed, because in the final target the silicon ether is not there. So, what you do? You basically cleave it with fluoride source. Now, fluoride source keep this silicon fluorine bond, will basically give you the enol back. Now, this enol is here, and this enol will try to neutralize its charge through this kind of resonance, and this is now very close to the target structure which you have drawn. Now, this minus will be now accepting the proton from this acidic source if you use some water, and will basically give you the. Now, this particular problem once came in the JAM exam, and this basically demonstrates a very nice way you can introduce different alkyl groups in a beta position to a alpha beta unsaturated ketone without using the standard Gilman or other reaction. So, what basically we did? We used triphenyl phosphine as a nucleophile to generate the phosphonium species. This phosphonium species acting as a basic salt. The enol phosphonium ion, which is now trapped with this TBS chloride to give the enol ether. So, this phosphonium salt now undergoes Wittig reaction with the aldehyde. This aldehyde was basically chosen based on the target molecule structure. Depending on the structure of the target, you chose this aldehyde. So, it will be something like this compound. Now, you cleave the enol silyl ether with this, you get the enolate, the simple anion relay, it comes here, and this is quenched up with this aqueous acidic condition, and you get your target molecule. The point is, this is a very nice demonstration of mechanism based strategy. Now, this mechanism is very simple, and then it will basically also giving you the idea that how key transformation or a, now this case you are basically generating a Wittig elite or Wittig salt in the reaction mixture by using a triphenyl phosphine as a nucleophile. Now, that basically sets up the entire thing. We will be trying to solve another problem which I believe is little bit complex, but the target molecule was this target. The starting material which was given, I have just given you a succinamide, sodium succinamide. Now, as time we do not have too much time, so we will just try to do the retro in a conventional way, and we say that this compound you can access from this way by simple doing a hydrogenation here. The CO2 can be reduced through LH, as well as this amide will be also reduced to give this amine, the cyclic amine. Now, the retro which I am drawing here is basically based on this succinamide structure. I say if this thing will now CH2 will give you a this kind of phosphonium thing as a minus, you can basically do a intramolecular Wittig. Now, trying to visualize this thing with the succinamide N minus, and this particular vitigillite has been chosen. Now, this is a very unique vitigillite based on cyclopropyl thing. The cyclopropyl, as I said, they are very unstable. So, this minus is symmetrical thing, this minus will basically try to attack one of this cyclopropane methyl group, and then it basically clips this particular thing to put a minus here, because this minus is stabilized by this CO2 group. So, if you do a standard nucleophilic addition on a cyclopropyl based vitic, this is actually commercially available. This is commercially available. So, what you do? You basically get this compound. After this opening, you get this compound. Now, this compound will undergo intramolecular vitic. Now, I say intravitic. Now, once the intravitic is done, you get this amide from this part and you get alpha beta unsaturated esters. Now, you simply doing a LH mediated reduction. So, this LH reduction will first give you this amide to amine, and then the CO2 will be also reduced to CH2OH. The double bond may remain here. You can just reduce the double bond with palladium charcoal and hydrogen. So, it is basically simple FGI. So, this transformation until and unless you know the particular this kind of vitic salts are commercially available, probably is difficult to design, but once you know that this kind of vitic salt exists, you can just think about the mechanism how this vitic salt, so this nucleophile can clip this vitic cyclopropane vitic and you give you a 2 carbon extension by this CH2 and this negative charge comes here because it is stabilized by this CO2 ET. So, by this way, by combining different mechanistical aspects of key transformation, you can basically design very efficient pathway of certain molecular entities and target molecules, which you have explained for this example. And a simple starting material like succinamide sodium salt can be used as a very good starting material to generate this kind of bicyclic nitrogen containing compound, as this compound is very much available in many of the natural products, many of the naturally occurring alkaloids. So, we will continuing our discussion in the next lecture. Till then, have a good time and just go through the assignments and try to solve those assignments, and we will be seeing you again in the next lecture.